Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration. Together, you and I must make our new agency
the most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything. We can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
The X-31 pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HAR.
An observation of an occultation is one of the more challenging missions that Sophia can do.
Right now, we are looking at the dawn of a new era of aviation.
Flight loads is a crucial discipline. It is one of the areas that requires a good combination of both science and art. We often say that every airplane that we have ultimately goes through the loads lab.
In 1964, a new building was rising from the desert shore of Rogers Dry Lake. The tests this laboratory has conducted over the past 50 years have supported almost every type of vehicle the aerospace industry has to offer.
We do a lot of testing in the laboratories to make sure that components are going to withstand the environments that they will see.
Every time we go away from the standard configuration on a vehicle, it changes the loads, and we've got to understand how that affects the forces and stresses and things going on within the airplane.
We in the Flight Loads Lab have been interested in thermal testing for many years.
These specimens are being exposed to temperatures from 400 degrees to 1,000 degrees Fahrenheit.
In order to precisely calibrate the thermal effects on the strain gauges, ground heating tests were conducted.
Also, over the years, there's been low temperature testing using cryogenic cooling capability.
A cooling system was used to lower the glove temperature to the minus 30 degree Fahrenheit pre-launch condition. The heating and cooling systems work together to bring the entire glove to cold soak condition.
The type of loads that a wing will experience in flight are bending loads, torsion loads, and shear loads. They're loads that are applied to the wings as a result of the air loads that are put onto the airplane when it's flying or when it's maneuvering.
How far can we push it? Where is it going to fail and how is it going to fail? So this work here has really been key to being able to help us anchor the models that we're developing to analyze the performance of these structures and also to take that next step and optimize the design of these systems.
The second HIMAT aircraft underwent extensive ground vibration testing after its delivery to the UL Dryden Flight Research Center.
Any aircraft in flight has resonant modes which occur as its structure flexes under aerodynamic loads. These flexures can become rapid and large. Under extreme conditions, they may even result in structural failure.
In Dryden's Flight Loads Research Facility, mechanical vibrators are attached to portions of the aircraft structure. As the aircraft structure is excited at known amplitudes and frequencies, its mechanical responses are carefully measured and tabulated.
So we're trying to understand how the airplane rings, basically like a bell.
You actually want to see the structural characteristics and how it behaves. Once you go and fly it, if you experience any flutter or dangerous vibration motions, then it's practically too late.
We can tell if the structure is sound.
With all this data, we'll be able to update our models, which will be used in our flutter analysis to validate that we are good and can give flight clearance for the vehicle.
In inertia testing, understanding basically how the mass is distributed around a vehicle, which gets important for the control laws.
The moment of inertia essentially tells us the angular momentum properties of the vehicle. We want to understand during flight, when we're trying to control it, how it pitches up and down, we'll understand how much resistance and inertia happens during those pitching maneuvers.
We need to know for certain that our sensors are behaving properly so that when we put them on our structures or put them on our vehicles, we actually believe the data that's coming off.
Not only test a large test article, but to bring in some new test techniques like the FOSS and really calibrate that against more traditional strain measurements and the finite element modeling.
The Flight Loads Lab here at NASA Armstrong performs some of the most sophisticated tests that I've seen on vehicles, flight vehicles as well as entry vehicles.
This facility is not only very unique, but it's a national treasure.